Welcome back, everybody. As I was saying, thanks, Rocher. So I'm going to tell you today about the Skolem, so state and prove the Skolem-Malher-Lek theorem. So finally, yeah, I think it's spelled like that, Malher. And because that's the same way the composer's name is spelled, isn't it? I'm pretty sure it's different Malher. One of these guys might be Polish, maybe Lek. Does that sound like a Polish name? Ah, okay. So it was proved, it's there and proved by two mathematicians and a beer. They're having a beer, maybe. So this is where the skolemoids, finally we come to the explanation. Just curious, who has heard of this Skolem-Malher-Lek theorem before? Just out of curiosity. No, nobody. Okay, good. So this is a very fundamental result in number theory, additive number theory. In what? Yes, yes, Anilifaiwa, yes. We found out what lipa means. It's a very basic result in number theory. And so I'll state it and prove it this morning. So let me just just by way of motivation, if you look at a polynomial in one variable. Actually, the other day we were asking if you have a polynomial with integer coefficient in one variable, is it decidable if it has integer zeros? I mean, we're just being very silly because if you have a fifth degree polynomial in one variable, right? So we know that it's going to go to minus infinity. Depending on the sign. Let's say it's a polynomial of the form, say, x5 plus something, then we know it's going to go to plus infinity. The x5 term is going to dominate. It's going to go to minus infinity as x is negative. And so, and you can place bounds from which it goes, above and beyond. So the zeros are, where you have the zeros is over a bounded space, and then you can just test, right? So the set of zeros of a polynomial is, well, we know it's going to be finite, especially in particular over the integers. It's going to lie in some interval. So if I give you a polynomial, its set of zeros is in one variable. Its set of zeros is finite, and now you can ask the question for this larger class of functions that we've considered. So we're looking at un n equals 0, n equals say 1 to infinity. A linear recurrent sequence, so you can think of this as a function from the integers from the natural numbers to the integers or to the rationals, and you can ask yourself, what of the set of zeros of f? So what of the set of n such that f of n is equal to 0? Okay, so we're interested in this set, and we know that linear recurrent sequences generalize polynomials, so it's going to be potentially a richer set of zeros. We know for polynomial this is always a finite set. Okay, and the Skolem-Malher-Lek theorem, which was proved in, it was proved several times. It was proved, I think, in the first time by Skolem himself in 1933 or something, or thereabouts. And then it was proved and then it was generalized by Malher, it was generalized by Lek. So one proved it for algebraic numbers, the other one proved it for over fields of arbitrary characteristic. But I'm going to show you the most basic version. And what's interesting is that apparently, the story goes that Malher was a reviewer of the Lek paper, which generalized the original Skolem theorem. He accepted the papers, and 3 years later, he wrote the same paper. He completely forgot that he'd reviewed that paper. And he wrote the same paper, I mean, basically the same idea. And the historians don't think this is malicious. Apparently, this is, all 3 of them are credited with this result now. Yeah, so this is...
Don't try this.
Don't try this at home.
So why is Malher before Lek in the list?
Yeah, Skolem-Malher-Lek. I don't know. It's always Skolem-Malher-Lek. I don't know. Honestly, that's a good question. Yeah. Yes. it's like, you know, disparity games is in quasi-polynomial time. So this was first proven by these guys, Kusinov and these other guys. It got Best Paper Award at Stock. And then Marcin, Brzezinski, and Ranko Lazic, you know, proved this result, the same result using these small improvement measures, you know, at Lix. Now, this paper was written after they knew of the Stock result, but their presentation came first because it came from the first day of Lix, and which was starting slightly before Stock. So they, you know, they presented it before before the other ones. Okay, so what does the result say? This set Z as a particular structure. Z is always a semilinear set, so one-dimensional semilinear set, and which means it always consists of a finite set, union, a finite number of arithmetic progressions, which actually, as it happens, all have the same period. So it's union, let's see, so I'm going to write this as C1 plus NZ, union dot dot dot, union CL plus NZ. Okay, does that make sense, this notation? By NZ, I think it's, sorry, yeah, I should say N times the natural numbers, of course. Okay, so just if the period is 10, then instead of going 0, 1, 2, 3, you will go 0, 10, 20, 30. So this is just the, so there's an offset, and then it's an arithmetic progression. Yeah.
F of n is equal to un?
Yes, yes, yes. I'm saying you can think of, yeah, you can, this is a sequence, and I'm just to compare it to polynomial, I'm saying think of it now as a function. Yeah, that's right. Yeah. Okay, does this make sense, what I've written?
I don't understand what this n, the big N.
So this big N is some number. So these guys are numbers. This is an arithmetic progression. So I'm trying to say this is, for instance, if C1 is 3 and N is 5, this set is going to be equal to 3, 8, 13, 18, da da da. That's what I mean by that. Finite, it's a finite set. Can you take, you mean N equals 0 here? You could, but it's the same N. It's always the same N, as it turns out, right? So it's not, yeah. You can always, that's true, it's always the case, yeah, okay. But what I mean, the reason I write it like this is because I'm going to explicitly show that this whole part is constructive. Okay, so it's going to have, I mean, you'll see how it comes about. But this part is non-constructive. And that's the mysterious thing about, well, the mysterious thing. That's extremely interesting, because if I give you a linear recurrent sequence and ask you, does it have infinitely many zeros? Then you can answer it. You'll see, because you'll say, well, you just look here. If any of these sets is non-empty, then yes, it has infinitely many zeros. It certainly has a zero and infinitely many, as it were. But suppose you find out this infinite part is empty, and this you can determine. Then you know that you have finitely many zeros. You know this for a fact, but you do not know if you have a zero or not. This is not known to be decidable. You know it's finite, but you don't know how to decide it. I mean, if you ask me, of course it's decidable. We just haven't, we just don't know how to do it. But it seems very hard. And so Terence Tao has written about this. He says it's faintly outrageous that we don't know how to decide this.
We don't know how to decide whether lambda is 0.
Yes, that's right. So I'll say more about this later on. I'll show you just a Skolem Problem. I haven't yet talked. This is just characterizing the set of zeros. The reason that, in 1933, the notion of this is decidable, not decidable, people weren't thinking in those terms. They were trying to characterize sets of zeros, right? But I'll be coming to that later. But the answer to your question, Moshe, is yes. We know some things, but not very much. And Terence Tao wrote about this in his book, Structure and Randomness. And he says it's outrageous that we don't know how to do this. And he says it means we don't know how to decide the halting problem even for linear automata. And these linear automata are these simple while loops that I had on the first day. And Dick Lipton also, he calls it a mathematical embarrassment, that we don't know how to decide these things. Okay, does this make sense, the statement of the theorem? Okay, so what I'll do this morning, I'll do this, and if there's some time left, then I'll do some more stuff. But this is what I'd like to show you this morning, the proof of this, this theorem for linear recurrent sequences over the integers. I think that's everything I want to say about this. Okay, so let's start. This will proceed. I'll have a number of lemmas. Let me actually just use the other board, in fact, so I can start on the left. And okay, so yeah, let me just recall. So let P be a prime number. So and we define for A in Z, VP of A is the highest power of P that divides A, right? So it's 0 if P does not divide A, and it's K if P to the K divides A, and P to the K plus 1 fails to divide A. And just for definiteness, it's infinity if A is 0 because P to the K divides 0 for any K. And now V of P to the A over B. So now this is a rational number. It's simply VP of A minus VP of B. And this is the p-adic valuation. Which is used extensively in various places. We'll be using this as a key tool. So this is, let me state the first lemma. So let P greater or equal to 3 be prime, and let DI dn n equals 1 to infinity be any sequence of integers. So this is not necessarily linear recurrent sequence, absolutely any sequence of integer. And let, write, Bn is the summation. So right, Bn is the summation for I equal 0 to n of n choose I, P to the I di. And the lemma says that if Bn equals 0 for infinitely many n, then Bn equals 0 for all n. Okay, so you look at this for a second. So you can think of it as slightly differently. Suppose you're trying to, you get to choose these di. You can choose any integers you want, positive or negative, and you're going to compute a sequence b1, b2, b3, and so on. And you're trying to make this sequence be infinitely often 0. Okay, so one thing you can do is say, well, take di equals 0, every di is 0, then bn is 0 infinitely often. But you're trying not to do this. You're trying to have some of the bn not be 0. And you get to choose the di. So you've computed, let's say, the first 17 terms, and then you get to choose d18. And you can choose d18 to be whatever you want. And you want to make this thing to be 0, you know, every so often. And this theorem says that you cannot. Okay? So if infinitely often the bn's are 0, it means the only way you can do it is that every di is to be 0. And so first of all, it's important that the di be integers and not rational numbers, because if they were rational numbers, it's completely clear that you could do this. And just intuitively, I'm going to try to say, I mean, we're going to prove this, but intuitively, the problem is that there's a p here. P is this prime number, and you're raising p to a high degree. if you're trying to make this 0, at some point you need to divide. You have to be able to cancel these p's. I mean, I'll make this precise. I mean, we're going to prove this. But basically, if you only have integers here, you cannot divide by p. And this is the problem. And this is why the use of the p-adic valuation is useful, because in the Euclidean norm, if you have something like 0.999999 and 1, you're saying that these two numbers are very close. But when you look at them p-adically, they're very different, right? Because the p-adic valuation, let's say the 3 valuation of 1 is 0, because 3 does not divide 1. But the 3 valuation of this term, 0.999999, it's at least 3, right? Because you can divide by 9, and then you have 1, 1, 1, and yeah, so it's at least 3. So you can see that with the 3 valuation, you can see a difference between those two numbers. They're quite so. So this is why we have to work with the p-adic valuation. Okay, does it make sense, this lemma, the statement of this lemma? Okay, so let's see. So I'll prove another lemma. So here's another lemma. If P is any prime and n is an integer, then the p-adic valuation of p to the n over n factorial is at least n times p minus 2 over p minus 1. And the proof is straightforward. So the p-adic valuation of p to the n over n factorial is going to be the p-adic valuation of p to the n minus the p-adic valuation of n factorial, which is going to be equal to n minus, and now I need to evaluate this thing. Okay, but let me just evaluate this thing. The p-adic valuation of n factorial is going to be equal to the number of times that p divides n, and then I have to take the floor of that, plus the number of times that p squared divides n, and I have to take the floor of that, right? Because those things can happen. Plus dot dot dot, and that is less than or equal to n over p. I drop the floors, plus n over p squared, plus n over p cubed, plus dot dot dot, which is equal to n times 1 over p plus 1 over, sorry, that should be p squared, 1 over p plus 1 over p squared, and so on, which is n over p minus 1, because you have a geometric series, right? So, which one? This one. So this is a product of numbers 1 to n. I'm trying to count how many times can I find p. So I'm going to find if n is say 100 and p is 3, then there are going to be 100 divided by 3 numbers that are divisible by 3, 100 divided by 9 numbers that are divisible by 3 squared, 100 by, does that make sense? But I'm only counting those once, because I've counted them here already. So because the p-adic valuation counts the power that divides, but I'm counting these guys. Yeah, does that make sense? Yeah, okay. Okay, so everybody's happy with this. So I get n over p minus 1. So this is less than or equal to. And so now this is going to be bigger or equal to, because it's a minus, and I have n over p minus 1, which is n times p minus 2 over p minus 1. Okay, so just the definition. Okay, so let p of x be a polynomial a0 plus a1x plus dot 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 plus an x to the n. Let this be a polynomial with rational coefficients. And I want to define omega sub k of my polynomial to be the minimum, either the minimum of v sub p of aj for j greater or equal to k, if k is less than or equal to n, and I want it to be infinity if k is bigger than n. Okay? So just the definition. And you notice, you can see, easy to see that omega 0 of a polynomial is less than or equal to omega 1 of a polynomial, of the same polynomial is less than or equal to. So the sequence the sequence increases as you increase the index. And so let now t be some integer. Then if you look at p of t and you evaluate the p-adic, this is capital P, this is my p-adic valuation. I apologize, my lowercase p looks like my uppercase p. So if I evaluate this, then that's going to be what? That's the p-adic valuation of a0 plus a1t plus dot 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 plus an t to the n, which is greater or equal to the minimum of vp of a0, vp of a1t, vp of a n t to the n, which is greater or equal to the minimum of vp of a0, vp of a1, vp of a to the n, which is equal to omega 0 of my polynomial. Okay, does that make sense? Are people happy with these inequalities? So this inequality here, in case you're wondering about it, you're looking at the, you want to know what is the largest power of p that divides this sum? Well, for sure, this exponent, this power, is at least the minimum of all these ones. Because if p to the k divides this term, if p to the k divides that term, if p to the k divides all these terms, then certainly p to the k divides their sum. So if you take the minimum of the vp of all these guys, then certainly you'll get a power of p that divides the sum. And now, in going from this to this, I'm dropping the t's because the p-adic valuation of the product of two integers is the sum of the p-adic valuation. Because whatever, if k divides, if p to the k divides a1, and p to the k prime divides t, then p to the k plus k prime will divide the product of a1 and t, right? So basically, by dropping these terms, the p-adic valuation, the p-adic valuation of a1t is certainly bigger than or equal to the p-adic valuation of a1 for t an integer. Okay, so this is how I get this this thing, and now a lemma, another lemma. So let p of x, q of x be polynomials with rational coefficients, and let n1 dot 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 nk be integers, if P of x is equal to x minus n1, x minus nk times, times q of x, then omega sub k of p is less than or equal to omega sub 0 of q. Okay, so I have my definition of the omega sub k here. I'm not going to prove this. This is actually just a simple calculation. And formally, if you want, it's approved by induction. So you can do it as an exercise if you want afterwards. I'm not going to prove it. It's straightforward. It's just by inspection, fundamentally. Okay? So just take my word for it. It's not, you don't see it immediately. You need to do a little bit of calculation. Let me skip that. Yeah? Yeah, so it's trying to look, I don't know if that's a good intuition, but basically you're trying to look at the p-adic valuation of disregarding the lower terms, right? The lower coefficient of a polynomial. You're trying to pick up the tail of you're interested in the p-adic valuation of the tail of your polynomial. Okay. And the reason that this equality holds is because P is fundamentally it's Q times a bunch of K more factors, which is why this thing holds, right? So it's not particularly surprising. So if you disregard the terms, the coefficient of the terms of degree lower than K in P, then basically you have something that's going to be less than or equal to yeah. It's going to come up in the proof later on. It's hard for me to say much more beyond that. Okay, does that make sense? Okay. So another lemma. So for each k, omega. Oops, sorry. Hang on a sec. Sorry, I just need to define this. So let n be fixed, and let R of x be the summation. So I'm defining polynomial from I equals 0 to n of di p to the I times x minus 1 all the way up to x minus I plus 1 divided by I factorial. So I'm defining a polynomial with rational coefficients. The di here are these the di's that you have in the statement of the original lemma, right? The sequence that's sort of given to you, and you're just forming this polynomial R of x, which for every n you've got a different R of x, and the claim is that lemma for each k, omega k of R is at least k times p minus 2 divided by p minus 1. Okay, so that lemma I will prove. Okay, so here's the proof of that lemma. So R of x, so let me just write it again. So it's a summation I equals 0 to n of di p to the I over I factorial of x minus 1, x minus I plus 1, which is the summation for I equal 0 to n of di p to the I over I factorial of the summation for j equals 0 to I of some number Sij x to the j. Okay, so I'm picking up the Sij here are picking up the coefficient of the, I'm collecting together the coefficient of the terms x to the j. And these Sij are integers. And it's actually interesting. There's somebody, I mean, I don't expect anybody to know this, but these numbers are actually called, does anybody know what these numbers are called? It turns out, I mean, I wouldn't have known this, but I mean, I've come across these numbers before. I wouldn't have realized that. They're Stirling numbers of the first kind. They're the so-called Stirling numbers of the first kind. So they come up in combinatorics. And so this I can write. So here I've got a summation from I equals 0 to n and j equals 0 to I. So just to draw a picture. So this is I and this is j. So I goes from 0 to n. Yeah. Yeah. The top on the top board.
Are you sure that the inequality is in the right direction?
Oh, did I get it in the wrong direction? No, I'm not sure. Let me check. Gosh. Let's see.
As you increase k, the minimum is over a smaller set.
Yeah.
So there is some intuition that he's right.
Yeah, no, it should be in that direction, yeah. Yeah, yes. Yeah, your minimizer is a smaller set, yeah. Uh-huh. Okay. Maybe, okay. Yeah, so go ahead. I mean.
Okay, so like x minus p.
X minus p.
Okay, so this is the first
Oh,
step.
bigger set. No, it's a bigger set. No, it's wrong. It's a bigger set. I got it wrong.
Okay, so this is the first coefficient, and q of x is like x squared times p.
Okay, wait, sorry. So p, do you want to come and write it? Okay, so that's your q?
That's my q.
Okay, so I just erase this.
Yeah.
Yeah, okay.
So like w0 of q equals 1.
Yes.
Yes. And my impression is that the w like 1 or w2 of p equals
1, because the x cubed coefficient is just p, so it's 1.
Yeah, the x cube.
No, you're pointing the wrong thing.
take the,
What's n1 and 2?
but I
Oh, hang on.
I take only the coefficients with small things.
Uh-huh.
No, it's the other way around.
Yeah. When you look at the x cube coefficient,
Yeah, but
there's going to be x cube p.
It's p.
x cubed p squared.
No, x
No, x cube. How are you going to get the x cube?
Tomek, what is your value of k and n1 and k?
K is 1.
And n1?
N1 is p. But the coefficient of x cube is x times x squared p, so it's going to be x cubed p. So
Yeah, but I don't. I think that the wk.
Yeah,
I
W1.
don't consider large numbers.
No,
yeah?
consider the large. Only the large ones.
only the large ones. You drop the small ones.
Okay. So,
No problem. It's actually useful because it clarifies the definition, I think, in everybody's mind, including mine. So thanks. Okay, so we're happy with that? Okay, so proof by counterexample not working. So let me just come back to this this sum. So first of all, everybody happy? I mean, moving from this step to this step, I'm just rearranging terms. So now I ranges from 0 to n, and j ranges from 0 to I. So this is the sum. This is, when I'm taking this sum, this is what I'm doing. And I'm going to switch the order of summation. So now j is going to range from 0 to n, and I is going to range from j up to n, okay? So I'm rewriting this as the summation from j equals 0 to n, the summation from I equals j up to n. Okay, I mean, I just make sure I don't make mistakes. Sorry, where was I? Okay, j equals, I to j to n of di p to the I over I factorial times Sij x to the j. Okay? And now, therefore, the coefficient, so the coefficient of x to the j is this term here. And so now if I calculate Vp of the summation from I equal j up to n of di p to the I equals j p to the I over I factorial Sij. So I'm trying to evaluate so for each j, now I'm trying to compute, I want to fix j, and I want to compute the Vp of the corresponding coefficients. I fixed j is fixed. Now I'm looking at the p-adic valuation of the sum from I equals j to n of d to the I p to the I over I factorial times Sij. And I'm claiming that this is greater or equal to the minimum over I greater or equal to j of the Vp of di p to the I over I factorial Sij, which is greater or equal to the minimum over I greater or equal to j. I'm going to drop the Sij of Vp p to the I over I factorial, which is greater or equal to the minimum over I greater or equal to j of I times p minus 2 over p minus 1, which is greater or equal to j times p minus 2 over p minus 1, because this is for I greater or equal to j. So everybody happy with this? In going from this to this, I've simply dropped this term Sij, which is an integer from the p-adic valuation. Yeah? No, the di are integers. Yeah. If the di are allowed to be rational numbers, the lemma is false. So di are definitely integers. Yeah, that's very important. Okay? Are we happy with that? So this is the proof of this this lemma, because the p-adic the omega k of my R is the minimum of the p-adic valuation looking from k onwards, and so because j now increases and I've got these inequalities, I get the lemma. Okay, so everybody okay with that? Okay, so now I can prove the main lemma. Okay, so the main lemma was saying that, if you remember, we had these terms Bn, which were defined as the summation of di. I'm just gonna make a mistake, so I'm just gonna. Sorry. What was it? It was the summation for n for I equals 0 to n. That's right. Of n choose I, p to the I, di. Okay, remember what the main lemma that I'm trying to prove says. I'm saying that if infinitely often these Bn are 0, then they all have to be 0, under the assumption that the di's are integers. And so the way that I'm going to do it, I'm going to say that I'm going to show the following. If Bn is equal to 0 for n in the set n1 dot 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 up to nk, okay, then the p-adic valuation of Bn is greater or equal to k times p minus 2 over p minus 1 for all n. Now, this will prove the lemma, because if Bn is 0 infinitely often, then the set is infinite, right? So k will go to infinity. And I'm going to show that for every term in the sequence, their p-adic valuation is bigger than k times something, so it's unbounded. So what conclusion can be drawn from this? Why would this prove the lemma? Yeah. If a number, if arbitrarily large powers of p divides a number, right? You're saying, you know, p squared divides a number, p cubed divides a number, p to the 17 divides a number. At some point, you have to say that number has to be 0.
It's not 1bn, it's a sequence of numbers.
Sorry? This is true for all n. This is true for b1, for b2, for b3. It's going to be true for all of them. So I should say then for all n, this is true. Okay? So this is my strategy. Okay. So how do I do this? Okay. So I'm going to write the following. I'm going to write again my r of x, which I probably erased now. No, it's right there. Okay, perfect. So I just rewrite it as here I equals 0 to n sub k. This is the n sub k of di p to the I x, x minus 1, x minus I plus 1 over I factorial. Okay, so that's my polynomial. And for t less than or equal to n sub k, I have r of t. This is an integer. I have that r of t is equal to the summation for I equals 0 to n sub k of t choose I, p to the I di, which is the summation for I equal 0 to t of t choose I, p to the I di, which is b sub t. Okay, so this t choose I simply comes from here. But now the sum goes all the way to n to the k. But I can actually stop the sum at t, because when I ranges above t, that thing becomes 0, okay? Because this product will include a 0 term. So this is what I have, and that's actually my definition of bt, okay? So now we're almost done. Now, since r of x has zeros at n1 up to nk. R of x has zeros at n1 up to nk because r of t is bt, and we're assuming that bn1, bn up to bnk are 0, right? So that means that r of n1, r of n2, and so on is 0. So it has zeros as this. So I can write the following. I can write r of x is equal to x minus n1, x minus nk times some polynomial q of x for some polynomial, and therefore the p-adic valuation of r of t is greater or equal to the p-adic valuation of q of t, and by the theorem that I've now erased, we have that the p-adic valuation, therefore, of bt, which is r of t, let me get this right. So it's equal to the p-adic valuation, so I'm going to write like this, r of t, which is greater or equal to the p-adic valuation of q of t, which is greater or equal to omega 0 of q, which is greater or equal to omega k of r, which is greater or equal to k times p minus 2 over p minus 1. Okay, this was this result that we thought we had a counterexample for earlier. Does that make sense? Okay, so I'll let you take a second to look at this. So this is the main, we've now proved the main lemma. The main lemma says that if this sequence Bn is 0 infinitely often, then it's identically 0. And from this, we will now prove the Skolem-Malloy-like theorem. So how do we do this? So we have a linear recurrent sequence un, which is given to us as, let me write a k minus 1 u n minus 1 plus dot 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 plus a1 u n minus k plus 1 plus a0 u n minus k. So I've just written it slightly different. So this is a linear recurrent sequence. And we will assume that a0 is not 0. Why can I do this? I'd have a shorter one, right? So I assume it's a linear recurrent sequence, so it's got some order, and the order will be the last a0 is not 0, okay? Right, so I assume that a0 is not 0. And so I know that, if you recall, I can always write un to be some v transpose m to the n w for some v transpose m and w. So this was the matricial form. You remember I did this on the very first day. And this m here was the companion matrix of the characteristic polynomial. And if you go back to the notes that I had at the time, you can see it's very easy to see. I mean, it's just from by inspection. The determinant of m is actually equal to a0. You just look at the construction. It was on the first column you had ak minus 1 to a0, and if you expand the determinant along the bottom row, you just get plus or minus a0. You just get plus or minus a0. Okay, so this is just by inspection, and therefore my matrix M is invertible. So choose a prime P prime, such that P does not divide A0. And now I'm going to look at the projection of M into Z P cross P. So I'm going to write MP. I look at ZP K cross K. So M is a K by K matrix. And I'm looking at the image of M projected into the field ZP. Okay? And I know that the determinant of MP computed in this field is not 0. Why do I know this? I'm saying the determinant of MP in ZP is not 0. Because it is a 0 which is not divisible by P. Okay? And therefore, I know that it's invertible. And I look at the sequence MP, MP squared, MP cubed, and so on. So that's a sequence that I evaluate in ZP k cross k. Now, in this sequence, I will have at most p to the k squared elements in ZP k cross k. And so at some point, two of these matrices will be the same. So I will have mp to the I is equal to mp to the I plus j. I know that mp is invertible. So if I multiply on the left by mp to the I inverse, I get the identity is equal to mp to the j. Okay? So there's some n. I'm just claiming that there's some natural number n, which is at most p to the k squared, such that mp to the n is equal to the identity matrix. That takes place in ZP. Okay? Right. What does that tell me about M? What does that tell me about M? This is mp to the n is equal to I. So it tells me that m to the n is equal to what? That's right. So I just want to check the notation I use. Yeah, so P times, call it M1. Okay? So there's some matrix M1, and this takes place now in Z K cross K. So this is honest to God. This is a real matrix, you know, in the real integers. M to the n is some identity plus P times M1. But the point is that now P times M1, all the coefficients in P times M1 are obviously divisible by P. Okay, so we'll be using that very shortly. So what do we have? We write. Take an integer n and write it as m times n plus a remainder r, where r is less than n. Okay, and we have that m to the n is equal to m to the little m, capital N, plus r, which is equal to the n m to the r, which is equal to the identity plus p m1 to the m times m to the r. And now I can write un, which is v transpose m to the n w. So that's v times I plus p m1 to the m times m to the r times w. Okay, I'll let you look at this for a sec. And so this m to the r w I'm going to call w sub r. It's just some vector. Okay. So I'm just going to use the other board. Okay, so I have that, just to write it again, un, which is capital N plus r is equal to v transpose I plus p m1 to the m times wr. Okay? Now, I can split this linear recurrent sequence un into n different linear recurrent sequences. So I want to write, let me just write it this way. So so for each r in the set 0, n minus 1, I can write I'm going to put the r here just to remind you. So this is I'm going to index it by m now. And I'm going to define this to be u sub m n plus r, and that's V transpose I plus P m1 to the m times WR. So that's just simply the summation I equals 0 to m of m choose I where was I? Sorry, m choose I, P to the I, V transpose m1 to the I, W. Okay, let's have a look. Thanks. Very good. Somebody is following. Yeah, okay. We're almost there. We're almost there. The punchline is coming. So I have the expression for every n, un is u, so that's my n. I've factored my n as m times capital N plus r, where r is the remainder. It is V transpose times this matrix to the m times this vector w. And for each r, I want to split this into capital N different subsequences. I want to split the sequence un into capital N subsequences. So for each r, I fix an r, and I'm just indexing now with r. And m now ranges from 1 to infinity. So this is a new sequence defined as u superscript r with sub m is defined to be that, okay, just by definition. And it's V transpose, this matrix to the m WR. This matrix to the m, I implied the binomial theorem. So it's m choose I. Obviously, the identity is just the identity. So it's going to be P to the I, m to the I put it there. I shift the vector because this is a scalar. So it got V transpose m1 to the I WR. Okay. Now, what are these guys? These are just integers that I can call di. These are integers. I don't know what they are. I don't even know what this matrix m1 is. I could compute it, but I don't, but it's some integers. So what do I have? I have that for each of my subsequences, it's either only finitely many times 0, or, by the lemma, it's infinitely often 0, because this is of the form that I had in my lemma. Okay? So what the conclusion is, the punchline is, for each, okay, for all r in 0, n minus 1, the sequence u to the r sub m, where m goes from 1 to infinity, is either finitely often 0 or identically 0. Okay? Of course, my original sequence un is simply the union of all these subsequences, right? Finitely many of which. So the result applies to the original sequence. But now I can see also constructively this last part. I mean, this computation of m1 and so on. I can do all these things constructively. This capital N, this m1 and so on. Pick a prime p that does not divide a0. I can do all this constructively. So I can determine whether a sequence is infinitely often 0 or not. Is identically 0 or not. How do I determine? I give you a linear recurrent sequence. How do I determine if it's identically 0 or not? Yeah? Sorry? Well, it's order k. The sequence is defined here. It has order, whatever it's going to be order k. The original order. So I just check the first k terms. If a sequence is identically 0, certainly the first k terms are going to be identically 0. But once the first k terms are identically 0, by definition, it's a linear recurrent sequence. The k plus 1 term is linearly dependent on the previous k. Well, if they're all 0, that's it. By induction, it's going to be 0. So I can check all these things. So I know which of the subsequences are identically zeros, and that gives me my arithmetic progression. Because this sequence, with these subsequences, when you insert them into un, they jump. They're jumping by n every time. So this is where my arithmetic progressions are coming from. Okay, does that make sense? Yeah? Any questions about this proof?
So where's the non-constructive part? It's the key lemma, right?
It's the what?
The key lemma saying that this Bn sequence will be either infinitely often zero.
Exactly. So, well, yeah. So this lemma just tells you if it's not identically zero, it's only finitely often zero. But it doesn't tell you how large this set is, or if there's an upper bound to. From that point on, it's finitely often zero. Fine. From that point on, it cannot be zero anymore. It does not say that.
No, but it's partly because there are you have arbitrary D's there. There's some, there's some part there that is kind of very general.
True.
But can you concretize it? There must be a way to concretize it.
Well, here the DIs are this. The M1 you can calculate. So the DIs, you know exactly what they are. Okay, still.
For specific DI, you should be able to get more information. You say if you take an arbitrary sequence, of course, you're not going to get to anything.
Yes.
But here you have something much more specific about because you know what M1 is.
Yes.
So you generalize it, and therefore you have lost the constructiveness here.
That's true. Well, okay.
But once you be able to go and zoom in.
This is why Terence Tao says it's outrageous. It's outrageous we don't know how to do this.
Well, but there is a recipe here how to go further. Go and look at this DI.
No, you can. But here's the thing. We're gonna do this. I mean, not today. I don't know how much time I have left. But I'm now going to talk about decidable cases of Skolem. Like, what do we know? What can we really do when we really look at these DIs? So this is going to be the
Moshe, in the spirit of today, sounds good, doesn't work.
No. I mean, you're right, Moshe. I mean, I'm not saying it's undecidable. But the thing is, you're saying we ought to be able to do it?
No, because you have, it's this VT, WR, and then you have the powers of M1, right? This is much more concrete.
So these DI are very concrete. But in fact, the original linear recurrent sequence is super concrete already. I mean, and what we're saying is that...
No, but there is now, we know where we lose constructiveness.
Yes.
You lose constructiveness because you say here, these are just DIs.
Yes, that's correct, yeah. Moshe is right, ultimately. This lemma is applied to general DIs, which are integers. Concretely, you know what the DIs are, but the shape of the lemma is still saying, it's a compactness theorem fundamentally. It's saying that if either you have finitely many, it's finitely often zero, or it's identically zero.
So I understand, but I'm trying to pinpoint exactly the point. So I understand it's in the argument saying that if VP of a number is arbitrarily large, then it has to be zero. And
yes.
This is the thing, right? Yes. This is where I think it's...
Yes, I mean, that sort of comes into it, yeah, I guess. Yeah. It's a bit mysterious. I mean, people yeah.
Curious. I mean, have people tried to say, okay, can we... Because again, we knew in some sense before that the argument rely on powers, and we can try to get more estimates there when we would be into zero.
Yes.
And we have this M1 here.
Well, how much time do I have left, Mikoi? 15 minutes? Okay. Yeah, I will tell you the story a little bit about this. Before we do this, any remaining questions on this proof? Was this proof clear? It's more or less. There are a few. Yeah. So. I mean, I guess if you're not used to dealing with p-adic valuations, this can be a little bit. I mean, one gets used to this. I mean, it's extremely useful. I mean, it's very widely used in number theory. But if you're not used to it, initially you're a little bit like, oh, these are a bit funny. Okay, so I'll tell you what the story of this is. So yeah, so you have a linear recurrent sequence. So we know what the set of zeros looks like. It's a semi-linear set. So for instance, if I ask you, could you come up with a linear recurrent sequence that has zeros at every square, right? So has a 0 at 1, at 4, at 9, and so on. Then you know the answer is no, because that's not a linear arithmetic progression. So we know things about this, and we are even able to decide if it has infinitely many zeros or not, because that part is completely constructive and everything can be done. So now I give you a linear recurrent sequence that has only finitely many zeros, and you try to decide, does it have a 0 or not? That's the Skolem problem. And the decidability of the Skolem problem is something people have looked at very hard. And so you can decide, so now what have people done to try to study this? As Moshe says, you try to look in, let's say, restricted, let's say.
I'm not even restricted. We know what the DIs are, right? This is an obvious place to zoom in.
If you prove this, Moshe, that's like, would be a major result, right? So let me tell you what people have actually done. So if you remember the order of a linear recurrent sequence UN, it's the number of terms that it depends on previously, right? So a Fibonacci is order 2 because every term depends linearly on the previous 2 terms. So if you look at the Skolem problem, so that's the problem. I'm just going to write it. That's the problem. So given UN, does there exist n such that UN equals 0? Okay, so does the linear recurrent sequence have a 0? So people have said, okay, what about order 1? And of course, this is trivially decidable, because order 1 is just a geometric program. You keep multiplying by the same number. Order 2, it's already not completely trivial. I think if you know a little bit of algebraic number theory, including some basic Galois theory, you can do it. It's decidable. It's actually folklore, so I don't know if you can pinpoint to. And now, what about order 3 and order 4? So this was open for a very long time, and this was finally shown to be decidable. And it was shown by Mignot, Shorey, and Tiedemann. So I'm going to write their names. So Mignot, he's a mathematician in Strasbourg. Shorey and Tiedemann. And also by Vereshchagin, who is a Russian mathematician. And this was done in the early 80s. So I think this paper might have been 84. Maybe this paper was 83. And they both showed decidability at order 3 and order 4. So what do they use in their proof? They use some algebraic number theory, a lot of p-adic techniques. But the key ingredient they use is Baker's theorem. Baker's theorem for linear forms in logarithms. And I'll talk about Baker's theorem next time, so I don't want to state it now. In fact, I may not actually state it, but I'll tell you what it does. And Baker's theorem earned him the Fields Medal in 1970. And we don't know a proof of decidability at order 3 and order 4 that does not, in some form or other, use Baker's theorem. So prior to, so he showed this theorem, I think, in 1968, or maybe 67. So prior to 1968 and 1967, it would have been impossible, at least in the present state of knowledge, even in today's current state of knowledge, prior to 1967, it would not have been possible to show decidability, even at order 3, which is remarkable, right? You take Fibonacci plus another term. In general, you don't know if the sequence is a 0 or not. You don't know how to decide that. I mean, I find that completely stunning. But using Baker's theorem, they were able to get order 3 and order 4. And then 10 years ago, actually 12 years ago, there was a group of 4 Finnish mathematicians that announced a proof of decidability at order 5. And many people know of this because when I talk about this, they say, oh, yeah, it's decidable up to order 5. It turns out their proof doesn't work, right? I mean, there's a major bug in it. And they've accepted this now. We've told them and pointed out and spelled it out and so on. The paper is still available as a technical report. In fact, I'm holding it in my hands. But because it has all this background and these nice, so it's actually quite a nice paper. But the proof of decidability at order 5 doesn't work. So right now, the best that we know is all the way up to order 4. And I was telling you yesterday, Moshe, so Richard Lipton has some very particular cases, an infinite set of cases where it's decidable when you assume something about the coefficient of the linear recurrent sequence, but a non-trivial thing, and this needs to be written up at some point. So because it's a nice result. But this is basically the state of the art on this problem. And I'll just say one last thing before I stop, because what I'm going to talk to you about the next lecture is I want to talk to you about the positivity problem. So Skolem, so let UN be an LRS, let's say over the integers. So Skolem asks, does it have a 0? And positivity ask, is it the case that for all n, un is greater or equal to 0? Okay? And maybe I'll talk also about ultimate positivity. I'll see how much time I have and so on. So ultimate positivity would say, well, I don't care about the first few terms, but eventually is it always non-negative? Okay. Now, when you look at these two problems, it's not obvious that there's a relationship, but actually there is a relationship. One is more difficult than the other. I just wonder if somebody can tell me which one. There's one of them, if you can solve that, you can solve the other. That's what I thought. This is why I attacked positivity a number of years ago. But it's the other way around. Positivity is harder than Skolem. If you can solve positivity, you can solve Skolem. Why is this?
So you can, I guess, shift it, replace 0 by 1, it should be equivalent? Or?
Well, and you're allowed to square.
And you're allowed to square. Very good, David. So you're trying to decide positivity of a sequence, so you can look at the sequence pointwise squared, let's say this, minus 1. So define Vn to be un squared minus 1. Now, Vn is less than 0, or rather, Vn is greater or equal to 0 if and only if un is not 0. Bearing in mind we're over the integers. Right? The only way that Vn can go below 0 is if this guy is 0, because then 0 squared is 0 minus 1, you go below 0. And otherwise, if un is at least 1, which over the integers, that's the lowest you can get, then Vn is going to be greater or equal to 0. So if you have a black box to decide positivity, you have a black box to decide Skolem. Okay? However, I'm now going to tell you something. This we can show is decidable up to order 5. So that's decidable for order at most 5, less than or equal to 5. So you think, oh, what's going on? I just told you that order 4. The problem is that when you do this construction, the order increases. The Vn now has order. And so you would have, in order to decide Skolem, so to decide Skolem at order 5, it turns out you need to decide positivity. You need to decide positivity at order 14, as it were. So it's square divided by 2. You just have to work out the details. It's not so mysterious. It's not quite square divided by 2, but that's how it is. And so, so positivity is harder, but at low order, we can go a little bit further. And I will tell you one last thing.
Do you know the reduction in the other direction? Is there
No. There's no known direction in the other direction. No reduction. And in fact, it's unlikely to be the case, and this is probably something I won't have time to show, but maybe I can just allude to it. If you had a black box to decide Skolem at order 6, okay, let me just, I'll just try to define it very quickly. There's these things called these Lagrange constants of like the Lagrange constant of pi. These are related to continued fraction expansion of numbers. And mathematicians are extremely interested in computing these Lagrange constants. And it's this big open problem, how to compute these things. And I don't quite have the time to stay. Maybe let's see how much time I have next lecture. But basically, if you had a black box to decide positivity of linear recurrent sequences at order 6, then you can start computing all these Lagrange constants for a countable set of transcendental numbers that mathematicians have absolutely no idea how to compute their Lagrange constants. So it's a hardness result, right? We're not saying we know how to do this. I'm just saying if you can decide it at order 6, then you can start solving problems that people have been You know, in mathematics, these things, people have been looking at these Lagrange constant problems for over 150 years. There's no such reduction for Skolem. Skolem tomorrow could be shown to be decidable, and you know, and it would actually affect anything. So positivity seems to be intrinsically harder. My personal suspicion is that they're both decidable. We just don't know how to do it. But you're not going to show decidability without some major breakthrough, at order 6 at least, and above, without some major breakthroughs in mathematics. And there's a weak converse as well. You're not going to show undecidability through some reduction from post-correspondence problem or something like this, because there's a weak converse that if you could show that it's undecidable at order 6, then it tells you something about these Lagrange constants as well. Basically, it tells you they cannot all be 0, because if they were all 0, then it would be decidable. So there's a kind of a weak converse. So basically, at order 6, it becomes hard. It becomes very hard in the general case. So what I want to show you next lecture is when you assume that the linear recurrent sequence is simple, or equivalently the matrix is diagonalizable, you can decide positivity all the way up to order 9. And in fact, if you could go all the way up to order 14, you'd get Skolem at order 5, even in the simple case. Anyway, so this is just you know, what I'll talk about, and I'll stop here.